Welcome to the first demo for Matt McCreary in our Ethereum for Undergraduate undergraduate education. Today we're going to be looking at Ethereum basic element structure and how they interact with everything, with code tracing to show how everything is linked together, to transactions in between accounts that's carried in the blocks that's located in the blockchain, and we'll show how the blocks are linked together, verified on the blockchain, and then anything inside is thus verified, and we can go in and dig into all the finite details of each of those transactions. So we're going to start up our Ethereum blockchain in full node mode, or we're on our full node machine, and we're going to get the block number. So we're going to have followed the setup where we create accounts, send a transaction, unlock the account, everything like that. That's already documented in the first lab instructions, just so we have blocks that have transactions, so we can take a look at the transactions inside all their fields. But we can check in my instance what block number I'm on. So we can type the command ETH block number. And that does not contain parentheses. And so we're currently on block number 226 for this blockchain. We can look at the last block in this if we do ETH block number and the number of the block. So if we go ETH, or is get block, and we put the block number in, so we go 226, and we're gonna get the contents of the block. So as we can see here, we have the total, or the difficulty of the block. We have any extra data that's hashed with the RLPX encoding technique. We have the gas limit for any transaction or anything that's handling the block. However, there's zero gas used, so this gas limit doesn't take into account. We have the hash of the block. There's no logs bloom. We don't have that in our environment set up, where I don't think Geth has it set up by default. So this will always be 0 in Geth as of right now with our current configuration. We have the address of our miner, who is doing the mining to not only provide the verification for each transaction and block, but they're also spending their computational power and getting rewarded for that too. So that's the address that they will get rewarded once they seal a block. So that is a type of account. It's just a miner account. We have the mix hash, so this goes into the RLPX encoding as well to get the actual hash for the block. We have the nonce that also goes into the RLPX encoding to get the hash. We can see what the parent hash is, so this should be the hash of the previous block. We can check that in a couple minutes. We have a receipt root, so this is the location in the tree where it's stored. It's also encoded with the RLPX. All of this stuff in here is going to be encoded with the RLPX, and it's encoded, not encrypted in Ethereum. That's something I learned this week, or it was defined clearly to me this week. We see the number of the block right here, the parent hash, the size of the block, our state root, which is the location of the tree where the genesis block is. We have the timestamp, the total difficulty, so this is how difficult it is to verify. It's a running number. It increases with every single block, which we can double check later in a couple seconds when we look at a different block. And we have the transaction root address right here. So if we want to see the previous block to 226, so 225, we can get the block 225. And so we have 226 up here, and we have 225 down here. So as we can see, the difficulty will always go up in between blocks. So since 225 is before 226, this difficulty is going to be lower than this difficulty. It always goes up no matter what. The gas limit also always goes up, and this is just increased as the platform continues to age and total time being used. Our extra data is the same, it looks like, in between the two. So it looks like the sender and receiver are the same, or there's no transaction in this block, or something very similar between this, where this looks like a normal block. As we said, the gas limit also didn't go up here for some reason. I'll have to look into that. But we still see where our miner address is, our mix hash, just like we see above. Our mix hash is different because it's a different block, and different values go into how they get the mix hash and the nonce, which go into the actual hash. So that's how we get the actual hash, and this is why they're different. But if we look at the hash of 225, it's 0xEE115C. We can make sure, or we can trace that to block 226, the following block, by looking at the parent hash. And we look at the parent block, which is the previous block, and we can see that the OXEE115C4 is also there. So that parent hash refers to this hash. So in this block 226, we have a parent hash, which is a pointer to the previous block's actual hash. We also have the same miner in both instances. Mix hash and nonce are different. Block number is different. Our parent hash, if we were to go look at block 224, the hash of that block would be this. Our receipt root is still the same. Our uncles is the same as well, and uncles are when you drop off the main chain but are still in the Merkle tree. So you're not considered off the chain, but you're not up to date on the current main chain. But you can always return to the main chain if you're an uncle. We see the size is the same between the two. See the state root is different actually between the two. Our timestamp obviously is going to be different because this one came after this one, and it seems that they were added very, very close together in time. And again, as we see our total difficulty increase. But in both of these, we see that there is 0 transactions in these. So we're gonna have to go back and find one that has a transaction. So previously I was able to send a transaction, and this is after I did all the configurations. I just wanted to do a fresh transaction where I sent 10 Ethereum from one account to another, just so I had a transaction queued up, so we could have taken a look at it. I do have screenshots of that, which I will present, but I don't have any queued up right now for the demo. But I can show you what a transaction would look like inside of a block. So I know that my transaction block is contained in block number 160, and that's just when I started the mining, it was the first block that was confirmed, and that was the queued up transaction. So that was in that first block. So since I know it's block 160, we can do eth.block get block 160. And we still have 0 transactions here for some reason. Oh, it's 154. That's the actual one. 160 doesn't have it. So yeah, we know. Oh no, that's the wrong function. So we're gonna do eth.getBlock, and we're gonna do 154 because that's the one that actually contains the transaction. Okay, so we can see that it contains a transaction in a second. So in 160, this one did not contain a transaction. I thought it did, but it didn't. It was 154 that actually contained a transaction. But we know that because there is 0 transaction in the transactions array. So if you were to go to a block that actually has a transaction, we can see the transaction hash in the transactions array right here. So I queued up 2 from one account to another account just twice. I just repeated the command by accident, but this is pretty cool because we can see we have queued up multiple transactions. So these are the transactions that we can go take a look at now. We can search by these hashes. These are the transaction hashes. Or we could just get the transaction by block number. So we can get transaction from block number 154, or we can get transaction and copy the hash string. So they return the same thing. We can verify they return the same thing from the block hash 0x54. We can see the from the account and the to the account are the same just because they're the same thing. But now we have a verified block that contains a verified transaction in between two accounts. So it's safe to assume that this transaction hash is searchable from any full node, which is true because that's how transactions are stored in the node history, in the general blockchain structure in general because of how they're linked together. But also because now we have two transactions. We don't know who owns the accounts, but we know who's sending, like what accounts are sending to what account. So just from taking a look at this one block, 154, and verifying that there's a 153 and 155 that are valid, we can validate that a transaction went through. We have the to and from accounts. We know how much gas was used, how much gas was sent, the hash of everything, and the value that was sent over. And these are just the values that any full node would be able to access when joining a network and downloading all the state tree data. So this is how you're able to search things in the blockchain from any node, as long as it's a full node or it has the same accessibility and privileges of accessing all the chain data as a full node. It's even more evident if you were to get block 0 and 1, where we can track everything. So if we were to go to block 0, this is the genesis block. We have our hash of the block, which it is the genesis block, but it does have a hash, so it will have a pointer for the first actual block that's not a genesis block in the chain. But the pointer will just point to this hash and say that's just the parent hash of the first block of the blockchain, which is the genesis block. Logs bloom, geth doesn't have the setup by default, I believe, so we won't see that. Mix hash will see change, the nonce will see change, the number will see change, and the parent hash will all see change in the second one, because that's when the environment assigns the ETH66 internal protocol assigns these values through RLPX encoding. We have the timestamp, which is 0, which is another indication is the genesis block. The zeros for the numbers also another indication is the genesis block. But if we were to take a look at the first public block, non-genesis, we can see that the parent hash, which is the same hash as this, ends in 59, starts with OXFBB, are the same. We now have a miner because that was configured in the environment. We have a mix hash, which is going to be used later, and we have a nonce for future encoding. And then we have our hash that's been created with some of these values down here. And we see the size is different because it has more information about the nonce and mix hash in the miner. The timestamp is different because it's not the first one in the chain. It's the first one added to the chain, just not the first one in the chain. And we see the total difficulty as well has gone up, as it always does throughout time. I wanted to get to Snap protocol this week and how it interacts, but I'm still trying to figure out how to capture it or use the logs for educational purposes. And I'm still working through ideas here on how to compare and how to work the questions. It's the first run through, and it'll get more refined as I go through and continue on working with other lab exercises in the future, but this is just a introduction to structures and how things work in the internal application level protocols of Ethereum for the education at the undergraduate level. Thank you very much.